welcome you for this first iteration of these half day tutorials on tipping. So we're going to be together, at least for some of you, until 5, I think. And we are having the pleasure of having Paul Ritchie, which will talk to us about early warning signs, which is one of the many faces of Paul Ritchie, which is a researcher at the University of Exeter for quite a time now. And well, I will leave you the floor. Thank you.
Oh, great. Thanks, Sasha. Thanks to all the organisers for the invitation to give this tutorial. So today I'm going to be talking about early warning signals, as Sasha mentioned, and this is like a technique that has been developed over the last couple of decades or so to try and forecast or anticipate when we might be approaching a tipping event. Well, first, what do we mean by tipping events or tipping points? These are where we observe large and abrupt changes in the output of a system that are typically caused by small changes to input levels or rates. And tipping can occur in many different fields. So one example is in the climate system. So here I've taken a map from the recent Armstrong-Mackay et al. Study in 2022, which did a review of the state of the art on Earth system tipping elements. And so here you can see various elements of the climate system that could be susceptible to undergoing tipping under global warming. This ranges from the melting of polar ice sheets, the disruption to ocean circulation currents, dieback of the Amazon rainforest, and disruption to various monsoon systems. But tipping isn't just restricted to climate. Like I said, it can appear in many different fields of science. And so here on the right hand side, we've got some other areas. So in finance, for example, with the market crashes, can also get it in medicine with the onset of epileptic seizures, but also in social systems where we might actually have positive tipping points where we might be trying to tip a system to help with mitigation on climate action. So you can think of the transition to electric vehicles as one example there. So how might we observe tipping in the real world? So here on the left-hand side, I've taken a simulation from the Hawkins et al. Study in 2011, where they forced a fully coupled climate model to tip the AMOC, which is the Atlantic Meridional Overturning Circulation. It's this large circulation current in the Atlantic Ocean that transports warm water from the tropics up to the North Atlantic. And it's partly responsible for giving Western Europe its relatively mild climate. And then as the water reaches the North Atlantic, it cools and becomes more dense. And so then we have a sinking or overturning there before the water is transported back down to the tropics via the base of the ocean. But under global warming, and predominantly from the melting of the Greenland ice sheets, adding fresh water to the North Atlantic could lead to a collapse of this, because adding fresh water will reduce the density of the water, and so it won't have this sinking effect and ultimately lead to the circulation collapsing. So in this particular study, they started with the AMOC in an on state, so we can think of this blue trajectory where on the y-axis we've got the strength of the AMOC as a particular latitude, and then on the x-axis is our faulting, which is here fresh water being added to the North Atlantic. And so as you can see that initially when you increase this freshwater faulting level, there's very little change initially to the strength of the AMOC, but there becomes this critical level in the freshwater faulting, beyond which we then observe this abrupt transition to some alternative state, here corresponding to the collapsed AMOC state. Now, a key feature with tipping events is this notion of irreversibility or hysteresis. And what that means is that if we were to retrace our steps and reduce the forcing, we can't recover the system back to its original state at which we tipped it in the first place. So this is what's being shown by this red trajectory, where they started with the AMOC in its off state, and then started reducing the amount of fresh water that's been added to the North Atlantic. And you can see that we have to reduce the freshwater forcing much further until we can recover our AMOC back to its on state. So that's how we might view or observe these tipping points in the real world or in complex climate models. And then on the right hand side here is how we can model this quite simply using a stochastic differential equation. So here on the y-axis we've got our system state, so this would be your variable of interest. It could be the strength of the AMOC, but it could also be carbon content in vegetation if we were to look at the Amazon rainforest. And then you've got your forcing parameter on the x-axis, which again could be your freshwater forcing, or maybe even more simply just global warming. And so we've got a bifurcation diagram for the system given by the black curves here, where the solid curves correspond to stable states of our system and an unstable branch given by the black dash curve. And so we have this region of bistability where the system can coexist in two different states based on its initial condition. So we can again imagine we start on this upper stable branch and we look at this blue trajectory. We increase our forcing parameter. We're just going to track this stable branch, and that is until we hit a fold bifurcation, at which point this upper branch ceases to exist, and that forces our system to transition to our lower stable branch. And again, if we started on the lower branch, you can now see that we have to reduce the forcing until we reach this other fold bifurcation on the left-hand side before we can tip back to the upper stable branch. And so this behavior that we might see in the real world, or these complex models, can really be quite nicely captured with such simple dynamical models. And so here's what such an equation might look like, a stochastic differential equation, where the first two terms on the right-hand side govern the dynamics of our underlying system. We then have some forcing given by this P of t, which we're initially going to just assume to increase or change at a linear rate given by the parameter r, which again, we're initially assuming this to be small. And then we have a stochastic term as the last term on the right-hand side, and this is to capture unresolved fast processes, and this gives our oscillations around our stable equilibrium state. Now, this is sometimes can be referred to as a gradient system for these simple models, where the right-hand side is the derivative of a potential function. So if we were to integrate the right-hand side, we get this stability landscape, which you see on the right-hand side, where the wells will represent the stable states of our system, a hilltop, the unstable state, and then we use a pool to indicate the state the system currently resides at. So as we play this animation and start on this upper stable branch, you can see that our right-hand well where we start is starting to shallow and soften. We get the emergence of a left-hand well. And then as we reach this fold bifurcation, our right-hand well disappears, and that forces our ball to transition down to the left-hand well. And then as we go back the other way, you can see that now as we approach the point at which we tipped in the first place, there's very little chance to get that ball out of the left into the right-hand well. And instead, again, we now have to hit this other fold where the left-hand well then disappears before our ball goes into the right-hand side well. Okay, so that's a very quick overview of tipping points, tipping events. What we're going to talk about today is how might we anticipate when we are approaching one of these events. And this is notoriously quite hard to do just by looking at some time series. So, for example, I've got 3 sample time series here, and I may ask you the question, can you identify how many of these time series would undergo tipping? And maybe also which specific ones might undergo tipping, if any of them do. So maybe we do a quick show of hands. Who wants to say whether the blue time series is going to hit a tipping event? Okay, a reasonable number. How about the green one? Yeah, and the red. And a few there as well. Okay, it's only the blue one that But as you can see, it's not always straightforward, and I don't know how confident the people that said blue and only blue were in that being the only answer. So there's been a lot of research in the last 2 decades to try and develop these warning signals. So on the left-hand side, just got illustration of how the theory on or the research on early warning signals has developed over the last couple of decades. So you can see there are only a few studies in the 2000s in ecology and climate, but really the rate of increase in research in early warning signals is exponentially increasing. And then on the right hand side, we've got various early warning signals that are being used to actually try and capture when we might be approaching a tipping point. Recently, there's been a lot of advancement in trying to see if we can use machine learning. So can we train the machine to tell us or separate trajectories that tip versus those that do not? But the main focus of today's talk will be looking at the 2 most commonly used early warning signals on the left-hand side here, which is the variance and the lag one autocorrelation. And what these statistical measures are designed to capture is this phenomenon known as critical slowing down as we approach a fold bilocation. And in fact, all the ones that are circled are trying one way or another, trying to capture this critical slowing down. So what is critical slowing down? Well, as we saw from before, as we are in this well and we're approaching a fold bilocation, this well is beginning to shallow and soften. And so what that means is when we're far away from the tipping point, the well is very steep and deep. And so if we make a perturbation to our equilibrium state, you would expect that the system won't transition very far, and it will also have a very quick recovery back down to the bottom of the well. But as the well then shallows and softens as we approach the tipping point, the same strength perturbation will now travel further, but also and therefore correspond to an increase in the variance you would expect, and also recover more sluggishly or slowly down to the bottom of the well. And therefore we would also expect to see an increase in the lag one autocorrelation. So how do we actually go about calculating these early warning signals? So typically we may just have some time series in an observable, but we need to remove the trend from this time series because a trend can affect, for instance, the variability of our statistics. So, and just because a system might have a positive trend or even an increase in trend, it doesn't necessarily mean it's on the approach to a tipping point. So what we really want to do is calculate these statistics around the equilibrium point. So we need to detrend the time series, and there's various methods that can be used to do so. One that's been used in this animation by Chris Bolton is to use a Gaussian kernel smoother. So this is the red curve being fitted or smoothing the data, the original time series data given in black on the top panel. And then we remove this to get our residuals, which are being plotted out on the bottom panel. And then we take a sliding window. So we take a portion of this time series, we look for or calculate our early warning signals. So the variance and being plotted here is the AR1, so the lag one autocorrelation. And then we slide this window across our time series and look for an increase in trend. Now we can sort of quantify this trend that we might observe by one method would be to calculate the Kendall tau. So the Kendall tau is a metric to determine how much a time series is either always increasing if it's close to +1 or always decreasing close to -1. But we can also look for whether we get a statistically significant trend. And we may construct that by looking at some control period and calculating the natural variability of these signals and then observing if our indicator goes outside a confidence window of our signal. And then we would say that we've got a statistically significant trend, and then we might be approaching a tipping point. Okay, so we can then go back to our 3 time series that we had from before. We can calculate the autocorrelation and the variance, and you can see with the blue time series that we do have an increase in signal in both indicators. Therefore, we would classify as approaching a tipping point, but with the red and the green, there's very little change, and so therefore we would successfully classify these as not approaching the tipping point. Okay, and so here's just a little example where early warning signals have been used to anticipate a transition in the climate past. So this is a study by Beatrice Arellano-Nava in 2022, where they used shells that can be found at the bottom of the Atlantic Ocean. And looking at the bivalves, so essentially you can think of these as like tree rings, which contain historical data about here, specifically the North Atlantic subpolar gyre. And you can get proxies from these bivalves. They tested the early warning signals on these different proxies, and they saw that they had increases in the AR1 and variance in 2 episodes leading up to the transition of the Little Ice Age, which corresponded to where the subpolar gyre collapsed. Okay, so far we've talked about how early warning signals can be used to anticipate that we might be approaching a tipping point, but prediction can take many forms, and we may actually want to be able to say at what particular time we might be approaching a tipping point. And so this is a study that I was involved with earlier this year with Peter Ashwin and Anna von der Hey and Robin Bastiansen here at Utrecht, where we looked at saying, can we actually quantify a tipping time? And in this study, we looked at the return rate, which is essentially capturing the leading eigenvalue of our system, and it can be calculated just from this autocorrelation given by the equation here. And then specifically, we looked at the trend in the square of this return rate. And that's because, just doing a bit of theory, but which I won't go into here, but when we have a linear forcing, we would expect the square of the return rate to decrease linearly as we approach 0, which would represent the fold bifurcation. And so we can imagine that if we have our signal up to some point in time, which we're going to call TP, the prediction time, then we could do a linear fit to our signal and extrapolate that into the future. And when that hits 0, we might say that's when we would expect to see tipping. But so here, what we're doing is we're wanting to say whether tipping occurs over a time horizon given by this capital delta, which you're seeing in these panels at the bottom. And so we calculate or extrapolate to the end of this window and see what our square of the return rate is. And then we could set a threshold, for example, 0, and if it's below that, we might class it as tipping. But we can tune that threshold how we want to either minimize false positives or false negatives. And so you can see this example on the left-hand side. We would need to choose quite a high threshold to classify this as hitting a tipping event within this time horizon, but the one on the right, you could have a much lower threshold and it would classify it as tipping. So here's one example where we've done that. So on the left-hand side, on the top panel, we've got our external forcing given by this lambda. And this is where we assume to cross a fold bifurcation when lambda equals 2 at t equals 0. You can see the response of our output variable x in the second panel. And so you can see we've got this tipping behavior shortly after we cross the fold bifurcation. Third panel is then our like one autocorrelation, and the fourth and final panel on the left-hand side is the square of this return rate. And so now we can play the game where we pick a time before our tipping point and we extrapolate our signal forward in time, and we can see whether we get tipping or not. So if we first choose our prediction time to be -40, we then apply a linear fit over this interval, extrapolate it forward in time, and we actually hit where we actually undergo tipping. But this is actually quite fortuitous, because if we were to make the prediction later at say -10 and do that same linear fit over the previous 20 time units, we would see that the tipping, or we would expect the tipping to occur much earlier. And so now we can consider a whole range of forcing profiles, some that stabilize before we reach the fold bifurcation, some after we cross the fold bifurcation. And we want to use this early warning signal to separate trajectories that undergo tipping versus those that do not. And so, like I said before, we can then use different thresholds to classify when we would expect to see tipping versus not. And this helps us generate these ROC curves that you're seeing on the top right. So ROC is receiver operating characteristic curves. And so you can choose this threshold to either minimize your false positives or your false negatives. But ultimately, you want to have some optimal threshold that minimizes both and pushes this ROC curve to the top left. So if we were right in the top left, we would have a perfect classifier where we would get no false positives or false negatives. And you can see that in these three different examples, which correspond to different prediction times that you can see in the bottom right, the stars and time horizons, we actually get quite a skillful early warning. And this is represented by looking at the area under these ROC curves. And so that's what's been plotted in color in the bottom right. And as you might expect, the closer we are to, or the later we make the prediction and the smaller the time horizon is, the more skill we have in our prediction. Okay, so that's all well and good, but there are things that obviously can go wrong with these early warning signals. And so here I've just listed a few things. So with this extrapolation, when we're extrapolating into the future, we're making some sort of assumption about what the future forcing is going to do. Is it going to just continue as it has been in the past, but it could turn around or stabilize before we reach that threshold? And so therefore, we might falsely predict tipping when it actually wouldn't undergo tipping. So we're going to look at some examples where extrapolation might fail. Another big issue is if we don't have a separation of timescales between what's the forcing, which is assumed to be slow, and the system dynamics, which I'm assumed to be fast. And this is because we're assuming that our system is in equilibrium, but if we're considering a strongly forced system, our system won't be in equilibrium, even though it hasn't tipped, and therefore we don't know whether we can clearly capture this critical slowing down phenomenon. And then we might have a totally different mechanism for tipping. So here, up to now, we've considered bifurcation-induced tipping and a slow passage through a fold bifurcation, which is what you'll find most studies on tipping points typically discuss, but you could be passing through a different bifurcation, such as a hop, and therefore you might not expect to see this critical slowing down, or you could have noise-induced tipping or rate-induced tipping, where for rate-induced tipping, it's more how quickly you're changing a forcing parameter rather than crossing any critical thresholds. And therefore, again, you don't know whether you would expect to see the same behavior. And then final one I've got here is we might have some properties of the noise that are changing. So we could have correlated noise, or the variability of the noise could be increasing. And so this could either suppress the signal when we're expecting to see one, or enhance the signal when we wouldn't expect to see one. And so these can lead to also false positives and false negatives. Okay, so extrapolation. Like I was alluding to, one issue could be when we have a non-monotonic forcing. So here we're taking what we call bump trajectory, where we initially have no forcing, then we start approaching the fold bifurcation, but we assume that the forcing turns around before we cross that fold. And if we have very little noise in the system, we therefore wouldn't expect to see tipping. So you can see in the second panel, we get no tipping behavior in our variable x. So we can then again calculate the AR1 and the square of the return rate. And now we can again play our game where we do a linear fit. So if we did a linear fit at -40, this is where we've got a stationary period in the forcing. So actually, again, fortuitously, we do predict that we won't hit any tipping event in the near future. But if we were to extrapolate whilst we were approaching the fold bifurcation, as we do at -10 here, you can see that we predict tipping when our system doesn't actually undergo tipping. And so, again, we can now consider various forcing profiles, some that don't cross the fold, some that do cross the fold and come back. And we can look at the ROC curves, and you can see that the skill in our early warning has decreased. And specifically this orange one, you can see it's pretty much lying on the 1-to-1 line, which corresponds to, you might as well just flip a coin to actually decide whether your particular trajectory is going to tip or not. And again, this is summarized in the AUC plot, area under curve plot in the bottom right, where you can see the colors are much darker. We're moving towards closer to 0.5, where we don't have any skill in our early one at all. Another issue with extrapolation is we might be outside the region of validity of our normal form. So imagine this scenario where we're on maybe the very upper branch and we're approaching fold A, but really we want to know about the information about fold B because the transition coming from that might be the one we're more interested in knowing about. But if we're on this upper branch, there's no way we can get any information that we are approaching the fold bifurcation of B. It's only once we would tip and enter this red box region would we actually be able to start to anticipate approaching B. And then also we might have a change in the leading eigenvalue. So here you can see we've got two eigenvalues, one that is constant and one that is quite large initially, but this is the one that is characterizing the fold bifurcation. Now, if you project onto the wrong eigendirection, you might be calculating this leading eigenvalue, and therefore you wouldn't actually be picking up any signal again that you're approaching a fold bifurcation until these eigenvalues cross over, and so you would get a very late warning in this instance. Okay, so that's some examples of where extrapolation could fail. Next one we're going to look at is this issue of separation of timescales. So typically we think of fast tipping elements. This is where we have our slow forcing and fast system dynamics. So if we were to think back to our climate system, where global warming has timescales of decades to a century, then this might be slow when we consider something like the coral reefs, which operate on years, maybe a decade. And there we get the behavior we would expect to see from before. So this is being shown in the middle row, where we're given it a linear increase in the global warming. We assume we have a fold bifurcation at 2 degrees of warming. We track this up as stable branch, but then as soon as we hit the fold, we get this instantaneous and abrupt transition to our alternative state. But at the other end of the spectrum, in the climate system, we have like the polar ice sheets. where these operate on the timescales of millennia. And so these are what we would call slow onset tipping elements. So now the dynamics are slow compared to the forcing. And so here on the bottom row, we've taken pretty much the same system. You can see the steady states are still in the same place. We've still got a fold bifurcation at 2 degrees, and we're still giving it this same linear increase in global warming. The only difference is I made the timescale of the system a lot slower in this bottom panel. And you can see that now as we cross the fold bifurcation, we don't see this instantaneous abrupt transition, but instead the tipping is delayed and we don't actually reach this alternative state until 3 degrees of global warming. And so what this opens up the possibility of is of having an overshoot of our tipping threshold, where we might not necessarily cause tipping. So here I've taken a conceptual model for the AMOC, which we've prescribed to have a threshold or fold bifurcation at 4 degrees of global warming. Now, if we give it two contrasting overshoot profiles, which are being plotted in the top panel, if we first look at the blue, this is where we have a relatively small overshoot at the threshold, but we spend a long time above the threshold before we bring the warming back down and converge to the 1.5 degree level. And so in the middle row, we get the behavior we may typically expect when we have our classical view of tipping points. And that is by going beyond a tipping point, we will tip our system. And then because of irreversibility, even though we bring the forcing back below the threshold, we can't recover our system back to its original stable state. But you'll notice with this other overshoot trajectory where we have a much higher peak in the global warming, but take a lot less time to get to come back below the threshold and converge to the 1.5 degree level, we can actually overshoot the fold bifurcation and prevent that system from tipping. And instead we recover back to the upper branch and retain the AMOC in its on state. And so back in 2019, myself and Jan Sieber developed some theory in the inverse square law, linking how far we can maximally overshoot a threshold and the time we exceed the threshold. And this was this relationship then can separate overshoot trajectories that cause tipping from those that do not. And you can see here the right hand side will depend on the effective timescale of the system as well as our stabilization distance below the threshold. And so in 2021, we went and used 4 conceptual models for different elements of the climate system, and we calculated these critical boundaries that separate tipping from not tipping for overshoots that are characterized by the peak warming and the time over the threshold. And so you can see that these boundaries are largely separated based on the timescales of the respective elements. So we've got the slow elements, the ice sheets, and the AMOC, where you can overshoot their thresholds on the order of centuries to maybe even millennia. Whereas faster tipping elements, such as the Amazon rainforest or the monsoons, you can only overshoot their thresholds on the order of years or maybe a decade. And then on the right-hand side, we can normalize both the overshoot distance with the stabilization distance below the threshold and the overshoot duration with the timescale of the tipping element. And you can see that all these boundaries collapse onto a single curve. And now you can see that we've got a really nice agreement between the numerically calculated critical boundaries, which are these solid curves, and the theory, this inverse square law, which is given by the black dashed curve. But the question is, can we now use this theory in the real world? Because in the real world, we won't necessarily know when we've crossed the fold bifurcation, which obviously we require to use this theory. Now, maybe we would intuitively expect this to be an easy problem. Surely we would know when we've walked over the cliff edge or had the rug pulled from under our feet, but it's not quite as trivial as that. And so this is what this animation is showing, is where we've got a fast system in blue and a slow system in orange. And then we can calculate our early warning signals as we're approaching the fault bifurcation. And you can see for our fast system, as we would expect, we see an increase in the lag one autocorrelation and the variance to signify we're approaching a tipping point. But for our slow system, we're seeing very little change in the AR1 or variance. And so in this case, even though we're having a delay in the tipping and we could potentially save our system by reversing the forcing, by looking at these early warning signals, we're actually not getting any information to signify that we are about to hit this tipping event. And so this is sort of linked to rate-induced tipping, because we're considering like strongly forced systems. And so with rate-induced tipping, this is where we don't necessarily have to cross any critical thresholds to cause our tipping. Instead, it's the rate at which we change our forcing that may cause the tipping. So you can think of this as a system's inability to continually adapt to fast changing external conditions. And so here we've got two sample forcing profiles on the top, where we start at the same initial level and finish at the same level, but the rate at which we get from A to B essentially is at different rates. So in blue, we've got a relatively slow rate. And so this is the animation on the left-hand side, where we just slowly ramp up the forcing. And you'll notice here the stability landscape doesn't change shape like it did for the stability, for the bifurcation-induced tipping, but instead we're essentially just dragging our stability landscape. And so as long as we do that sufficiently slowly, we can keep our ball in this original state, the left-hand well. But if we now pull our stability landscape that little bit further, as we would faster on the right-hand side, you can see that now as we drag it, the ball rises up the side of the well, over the hilltop, and then we tip into our right-hand well and undergo rate-induced tipping. Now, because we don't see any change in shape of our stability landscape, it's not clear whether we would necessarily expect to see early warning signals for this rate-induced tipping. And when you calculate the early warning signals temporally, like we've been doing using a sliding window, we don't actually see any early warning. But what we do see is signs of a spatial early warning signal. So this is something I looked at back in 2016 during my PhD, where we use the Fokker-Planck equation, which describes the time evolution of the probability density function. And so then we can calculate our statistics off of that. And so this is essentially like a spatial early warning signal, because you can think of this as setting a lot of initializations, giving it the same forcing but different noise realizations, and then calculating the statistics on that. And so one advantage maybe of spatial early warning is you can substitute space for time. So if you don't have a very long record where you can calculate a temporal early warning signal, if you have a lot of data points, maybe a spatial early warning signal could be more beneficial, because you don't need to use the sliding window. Anyway, so in this example, we calculated the autocorrelation and the variance, and here we have the fastest change in our external forcing occurring at t equals 0. So if we were to look at the early warning signals up to that point, so this green dashed line, we'll see that we get an increase in the autocorrelation, but we don't actually see any change in the variance. And so we wouldn't actually necessarily be able to classify it as approaching a tipping event. But then we calculated the most likely transition path to have rate-induced tipping. And what we observed is that the most likely time for tipping actually happens after we have this fastest change in forcing. And this is about 1.5, the red dashed line. And so if we looked at the early warning up to that point, we do indeed see now an increase in the lag one autocorrelation and the variance. And so, yeah, this sort of signifies we might be able to use spatial early warning signals for rate-induced tipping, although this is essentially where we don't have any coupling between these different realizations. Maybe if we have a strongly coupled system, it might also fail. And so just to finish, I wanted to give an example from a fully coupled climate model runs. And so this is a study by Chris Bolton in 2013, where they looked at I think it was a single model run of Amazon dieback. So they took out three key variables. So broadleaf fraction, so you can think of that as tree fraction, BC, which is the carbon in the vegetation, and MPP, which is net primary productivity. They then calculated the early warning signals on these three different variables, and they didn't actually get any coherent signal that there was to be simulated Amazon dieback. And so what they did in this study, and what we've done since in the more recent generation of climate models, is look for what we call system-specific early warning signals. And this is where we have some mechanistic understanding of the system itself that might be able to help us understand when we might be approaching a tipping event. So with the Amazon rainforest, you may know, but more than half of the precipitation that falls in the Amazon is generated by the Amazon itself. So we've got this moisture recycling, because rain that falls in the Amazon, it gets intercepted by the trees, and then this gets evaporated or transpired back into the atmosphere, and then that falls again as precipitation. But if trees were to start dying, whether that's through increases in temperature or drying conditions, then you can imagine that less of the rainfall will get intercepted. So there will be less of this moisture recycling, and this will generate positive feedback, leading to the abrupt dieback of the Amazon rainforest. But evaporation also has a cooling effect. And so what we then looked to do is whether we can see a signal in the temperature seasonal cycle and the amplitude of that. Because in the wetter months, there wouldn't be really much detected in terms of the change in the evaporation, because there's still plenty of moisture about. But in the drier seasons, we would expect to see higher temperatures. And so this is a study that Isabel Parry, a PhD student in our group, looked at 7 different climate models in an idealized scenario of increasing CO2 by 1% per year. And she identified 4 models that at least have very coherent regions of where we see abrupt Amazon dieback. And so here's some sample time series from 3 of those models, looking at the vegetation carbon, and you can see that we've got very clear abrupt dieback events. And then on the right-hand side, we've plotted out the temperature seasonal cycle amplitude, and you can see that is increasing in these specific examples. But then the question is the temperature seasonal cycle only increasing in those that have Amazon dieback? What about the other grid points that don't feature Amazon dieback? And so we looked at calculating the sensitivity of the temperature seasonal cycle to global warming in all these 7 models. And the purple bars correspond to where we don't have any Amazon dieback, whereas the red grid points do have some future dieback event. And what you'll notice is in the 4 models that identified these coherent regions of dieback, there is a threshold in the sensitivity that if we were to exceed it, then we would be confident in terms of identifying that particular grid point will undergo future dieback. And even when we combine all the models together and look at the bottom right plot, you can see that if the sensitivity is sufficiently high, we would have a decent chance of that particular grid point experiencing dieback in the future. And so just to summarize, we've talked about early warning signals, which is a technique that has been developed recently to try and anticipate these upcoming critical transitions or tipping events. Two of the commonly used early warning signals are to observe an increase in the lag one autocorrelation and variance, and this is to try and pick up evidence of this critical slowing down phenomenon that we would expect to see as we approach a fold bifurcation. And these generic early warning signals are quite appealing because you can just take your favorite time series, right, apply these early warning signals and see if you see a trend in them, and therefore potentially may give you an inkling as to whether you're approaching the tipping point. But just a word of caution that these signals are susceptible to false positives and false negatives. So you need to really be careful when using these signals and be concerned about issues such as extrapolation, timescale separation. Do you have the correct timescale separation? And also maybe changes to the noise properties. And then we just touched on at the end there, maybe looking at also system-specific early warning signals, and so maybe we can think about deriving these if we have some mechanistic understanding about your system of interest, and that might be able to give you maybe a more robust early warning. And so with that, I'd like to finish. I'll just leave some references up for those that are interested, but yeah, thank you for your attention.
Thank you so much, Paul. So we have plenty of time for some questions, if you have some. Don't be shy. Oliver?
Yeah, thanks. Very nice overview. I was wondering, I mean, one of the limitations that I can also imagine especially in the tipping time estimate, was that you show a time series that had a relatively high signal to noise ratio, right? If that decreases, is there some kind of, noise level where you really cannot detect anything anymore from?
Yeah, exactly. So we didn't actually look at that in that particular study, but you are dead right. So we just assumed that the noise is very small, and it's like you're comparing the rate of forcing to the level of the noise, right? And so if you have the noise so large, you might actually expect the tipping before you hit the fold bifurcation, and so indeed it is another aspect that can go wrong. Definitely wasn't an exhaustive list that I gave.
I can ask a question. So the point is that early warning signals for complex systems. So it's a bit challenging because how do you define the state of the system? Then you can say, okay, the state that much change, that is a tipping point.
Yes.
So
so there's, I guess, lots of questions about whether you have tipping dynamics in like a complex system. And maybe one of the arguments could be that if you do observe your early warning signals, maybe that could be an indication of tipping behavior. But yes, it's definitely an open question, right? In terms of whether in a complex system you can sort of classify an abrupt change as tipping behavior. What I like to do is, if possible, be able to force your system very slowly in both directions and look for this hysteresis behavior. But obviously, the more complex your model, the longer these simulations take and more expensive to run. So, but that's definitely a good point.
Maybe to add up on that, so I think I understand how the lag one and the variance work for one-dimensional systems. But when you have a multi-dimensional system, what is supposed actually to show this increase in variance and autocorrelation? Is it each variable or just?
Exactly, it depends. You need to be looking in the right direction. So I think Johannes Lohmann's done a study quite recently where if you look in the wrong direction or the wrong variable, essentially, you might not see any early warning. But
Okay. So suppose we have good states representing the system. But this window based. So what window size is it?
Yeah.
So
That's part of the exercise I'm looking at, but yes, I think, yeah, the window size is quite arbitrary. You sort of want to make it large enough that you can capture large enough for the timescale of the system, so you can capture the intrinsic variability of that system, but you can't make it too large because you need to assume some sort of stationarity. So it is a bit of a trade-off. And yeah,
what the problem with complex adaptive systems is that we don't know if we complying with that.
yeah.
So is there any alternative rather than window-based methods? That's all we don't consider it like this.
So if you have spatial data, you don't necessarily need to have a window. But again, it's a question whether spatial signals also work. But also, like I said near the start of the talk, there are these maybe machine learning methods that have been, but I haven't worked in it personally, but maybe that can also give some insights.
Anyway, also even if you use machine learning, deep learning, so at the end, if you are considering time series or a spatial temporal, anyway, so we are still going through a window. So
Yeah.
Sorry. Are there studies like which have looked at this influence of this window size on early warning signals?
Yeah, so I'd say a good reference to look at is Ditlevson and Ditlevson 2023. So this was like quite a famous paper in our area, wasn't it? In terms of it tried to predict when the AMOC would collapse, but within that paper, they actually talk about how you might choose the window. So that's probably a good source to look to.
And also when you talk about this fast system versus slow system, this overshooting phenomena.
Yeah.
So what do you mean, like the rate of change is faster than the system dynamics, or like what is this fast system versus slow system?
Yeah, so it's basically you've got the timescale of the forcing, and you've got the timescale of the system dynamics itself. And so for a fast system, the fast essentially means the timescale of the system. So if it's a fast timescale, like a short timescale, and the forcing is over a much longer timescale, then it's a fast system. Whereas the slow system is where you have like a long timescale of your system, and the forcing is therefore comparatively fast.
But in both the cases, the bifurcation diagram remains the same. So I assume
Yeah,
that the parameters.
So basically, you can think of it as one system has a lot more inertia, and therefore it may be more sluggish to respond just naturally. So let's maybe go back to it.
So like the model parameters are also the same, right? In both the system, like otherwise, how do you?
Yeah, so these states are the same, but actually on the stability landscape, you can see these values are different. And so that's where I guess you can sort of see the differences between the two systems.
But when we say fast at the level of the system dynamics, it essentially means the attraction rate to the table field, right?
Yeah, exactly. Yeah.
Ike?
I wanted to ask about the early warning signs that don't rely on critical slowing down. You had an overview of you at the beginning, and could you comment a bit more on those when they could be useful or what their differences are? It looks like they're
So yeah, I think is that third one skewness. So this might be. I mean, some of these I actually struggle to classify. Is this really actually just picking up the early warning? But like with, the critical slowing down or not. But like for example, with skewness, you might one side of the well is flattening more than the others, right? And so therefore you might be able to be picking up a skewed signal. I mean, I haven't myself really looked into many other early warning signals than those I've discussed on critical slowing down.
or is there an alternative general idea behind them compared to a changing landscape, because the idea of critical slowing down, and then as you said, if you extend it to skewness or so, is all you try to detect changes in your stability landscape.
Yeah, I mean, for like the spatial early warning signals and the rate-induced tipping, I'm not sure that's necessarily picking up critical slowing down, right? Because our stability landscape isn't changing. I actually haven't quite got to the bottom of why we are necessarily seeing those signals still. But yeah, I can't really comment too much further. Yeah.
So in the work you had with Peter Ashwin, they also considered white noise as your system when you looked at?
So white noise.
Yes.
Yes, yeah. So we use white noise predominantly in that. Yeah.
You said something about noise repetition.
So you could also have correlated noise or noise that has like an increase in variability as you approach the fold bifurcation. Or well, let's say you're not approaching anything and you've just got a stationary system, but the variability of your system is increasing, then you would obviously get a variant signal, but you might not have the AR1 signal. So, but you do have to really be careful about understanding your noise in the system, because there could be certain noise types that do give you both an increase in the AR1 and the variance, and yet you're not actually approaching the tip of them.
That's why I was curious, because the variance and the autocorrelation are based on the delta from the white noise that you get back, and you don't have that with color noise.
Yeah.
So what method do you normally use when you don't have white noise? And for example, how would you extend the methods that you look at with Peter Ashwin's in this paper when you have color noise?
Yeah, good question. I'm not sure I know the answer. So I think Andres Moore did a recent paper on looking at red noise, and so I would probably refer you to that study.
That's fine.
Yeah.
Maybe a last question. Do you know of similar statistical methods that can diagnose when a system is beyond the tipping point, like just diagnose the out of equilibrium?
So this is something we're currently trying to work on.
Are you? Okay.
Yeah, so Isabel's our PhD student is looking at that.
I guess it makes sense also with this inverse square law thing.
Exactly. It's something that's bugged me for quite a while now.
Okay.
We've got this very nice theory now, but we can't really use it.
So you don't answer us.
But yes, no, it's something we're
Okay, cool.